Okay, thanks very much, Athenios, for the introduction, and also thanks to all the other organizers of ZORP. So yes, I'm going to be talking about sums of 4 Squareful numbers. So first of all, we say a non-zero integer n is Squareful if for any prime p dividing n. We also have the p squared divides n. So for example, any square number would be automatically Squareful, but we also have things like 72, because when you look at the prime factorization, all of the exponents here are at least 2. Now it's quite easy to show that every non-zero Squareful number n can be written uniquely in the form x squared times y cubed, where y is a non-zero square-free integer and x is a positive integer. We'll use this again later, but for now we can use it to estimate the density of Squareful numbers. So to do this, we fix the y, and then we count the number of x's such that x squared times y cubed is bounded by b. And then we can take a sum over the y's, and we end up with a constant times b to the half. And if you did this more carefully, you could get an explicit Euler product for that constant. Anyway, here's the main counting problem for the talk, and it's nkb. This is defined to be the number of non-zero integers z1 up to zk, which are all Squareful. They're all bounded by b. They're co-prime. And then so far this would still be fairly easy using the kind of arguments above. But then we add in an extra equation that the sum of these has got to be 0. Very naively, we might guess that nkb should be like a constant times b to the k over 2 minus 1. This is because we've got b to the k over 2 choices up to a constant for these Squareful numbers z1 up to zk. And you might guess that the probability that they sum to 0 would be like 1 over b, which gives you this minus 1. All right, so one geometric motivation for considering this counting problem comes from Campana points. And the sort of slogan here is that Campana points provide a way to interpolate between rational and integral points. So we let k be a field. For us, this will just be the rational numbers q. And we define a Campana Orbifold to be a pair xd, where x is a smooth variety over k, and d is this divisor. So it's the sum of the prime divisors d alpha, and we have weights epsilon alpha. We assume that epsilon alpha takes the special form that it's either 1 or 1 minus 1 over m alpha for some integer m alpha, which is at least 2. We also assume that the support of this divisor has strict normal crossings on x. In order to define Campana points, we then need to fix a good integral model of this over OKS. Here S is some finite set of bad places which contains all the Archimedean places. Then the Campana points are the k-rational points on x, such that for any alpha and for any good place v, the intersection multiplicity of p and d alpha at v is either 0 or it's at least m alpha. So we can show, this is what I meant by the first bullet point. In the middle here, we've got the set of Campana points, and then they contain the integral points, and they're contained in the rational points. So the left-hand inclusion here would be an equality if all of the epsilon alphas are equal to 1. And the right-hand inclusion would be an equality if all of the epsilon alphas are 0, or in other words, like the divisor D is 0. Okay, and then we also have a notion of thin sets for Campana points. So first up, I'm just going to recall what thin sets are for rational points. Given an irreducible variety X over K, a subset A of the rational points is type 1 if A is a proper closed subvariety, and type 2 if A is the image of a dominant morphism of degree at least 2 of the rational points on some other projective variety V, which has the same dimension as X. Yeah, and then the thin set of Campana points is simply the intersection of a thin set of rational points with our set of Campana points. In 2019, Piero Pan-Smits, Tanimoto, and Verily Alvarado formulated a Manin-type conjecture for Campana points, which I'm going to call the PSTV-A conjecture. So it says that if XD is a Fano Campana orbifold and H is a suitable height function, then provided we allow ourselves to remove a thin set T, then the number of Campana points of bounded height should behave like a constant times b to the a times log b to the b minus 1. And here in the paper, they describe explicitly what these A, B, and C are on the right-hand side in terms of geometric invariants, which have quite a similar flavor to in the classical Manin conjecture. All right, so yeah, I'm now going to explain how this counting problem NKB fits into this picture. The first bullet point here is just a reminder of what Campana points are. And then in our example, what we do is we take X to be projective space over Q, and D is the divisor where we've got all of the weights are 1/2. So that means all of the M alphas or MIs would be 2. And then the DIs consist of all of the coordinate hyperplanes, and then this extra hyperplane defined by sum. Okay, and then we have to choose a height, and this is the height we use. So it's maybe slightly different to the usual height on projective space. But this final factor of the sum of the coordinates here, it's really just for convenience. It doesn't make too much difference. And then the intersection multiplicity of Z with D1 up to DK at a prime P is precisely the p-adic valuation of these points. Because all the M alphas are 2, that's saying that for all primes P, these p-adic valuations are either 0 or they're at least 2. And that's that holding for all primes P is precisely saying that these things here have all got to be squareful. So this is where like the squareful condition in our counting problem NKB comes into the picture. Then if you work out what the constants A, B, and C are in this case, it turns out that the PSTV-A conjecture is predicting that NKB is like a constant times B to the K over 2 minus 1, a bit like our naive heuristic said. Although this is after the potential removal of a thin set. So I'm now just going to summarize a few of the known results of the PSTV-A conjecture from the literature. First up, NKB has already been dealt with by Van Valkenburg in 2012 for any K at least 5. When K equals 3, this problem seems extremely difficult. And at the moment, we only have the following upper and lower bounds. So we're expecting the lower bound to really be the truth here. but it seems very difficult. In a slightly more general setup, Browning and Yamagishi considered hyperplanes in Pn, where now not all of the mi's are 2, so this corresponds to looking at mi powerful values of things. And they just have this condition that n is essentially sufficiently large in terms of the mi's. Then in the paper where the PSTV-A conjecture was introduced, they established it for vector group compactifications. We have split toric varieties using a very general version of the hyperbola method developed by Campana and Schindler. By equivariant compactifications of the Heisenberg group. And then finally, Sam Streeter studied powerful values of norm forms. Okay, so one thing that's missing from the first 2 bullet points here is the case k equals 4. So this is what I want to talk about now. Here's a reminder of what the counting problem N4B is. And according to the PSTV-A conjecture, we're trying to end up with something which is a constant times b here. But in fact, if you look at N4B itself, then it's greater than b log b. To see this, what we do is we use this decomposition. So we're writing each of the zi's as yi cubed times xi squared. And then the equation that the sum of them has got to be 0. If we fix the y's, this then becomes a quadric. Okay, so then N4B is a sum over these choices of y of nyb, and this is our nyb. But the thing is, even just for like one fixed choice of y, we can get a contribution of b log b. And this happens precisely when the product of the yi's is a square. This is essentially just Manin's conjecture applied to the quadric, which we definitely know is true. And the point is that when the product of these coefficients is a square, then the rank of the Picard group is 2, which gives us this extra log b factor. Motivated by this, we define a set T, and this consists of all of the non-zero integers z1 up to z4, which are squareful, copine, sum to 0, and also such that their product is a square. The saying that the product of these is a square is the same as saying the product of the y's is a square. So this is the set that we're going to have to remove if we want any hope of getting a constant times b in our asymptotic. And here's the main theorem that we proved. It says that this set T is a thin set of Campana points, which means we're allowed to remove it according to the PSTV-A conjecture. And if we do remove it, then the count N4B becomes this thing which I'll call NB. And the theorem says it's a constant times b, and then a small power saving in the error term. Okay, so yes, in contrast to the case when k is at least 5, we do have to remove a thin set here. So Van Valkenburg didn't have to do that. Anyway, I'm just going to very briefly try and sketch the proof. We've kind of already done the first stage, which is to write this NB as a sum over the y's of the NYB. And this is precisely what I had on the last slide, but I've added in the condition that the product of the y's is not a square. And then, yeah, so at the bottom of the last slide, we found an asymptotic for NYB for each y. But the trouble is that the error terms here are going to depend on y. So really the challenge in proving this theorem is to get enough uniformity in our estimates for NYB that we can actually take this sum over y and maintain a good enough control over our error terms. in order to tackle this problem, we considered a slightly more general situation where this is n primed AB, and we're counting points on a diagonal quadric where the maximum of the monomials is bounded by B. And we want an estimate for this where we keep track of the dependence on the coefficients AI. Then when we apply this to our theorem, we're essentially taking AI to be yi cubed. Okay, so this is what we did, and here's the main auxiliary result. So in order to prove this, we used a version of the circle method, first introduced by Duke, Friedlander, and Waniek, and further developed by Heath Brown in his 1995 paper. And yeah, I don't really have time to go into much detail, but it's like a smoothly weighted version of this. So we have to introduce a smooth weight W, which approximates the characteristic function on this cube. And then the kind of starting point for this is that n prime WAB satisfies this estimate here. And it involves an exponential sum SQAC and an exponential integral IQAC. And what we show is that the main term comes just from when C is equal to 0. And then we have to find estimates for the exponential sums and integrals to get all the other values of C as an error term. Then once we've done that, then we have to remove the smooth weight again to actually get an estimate for asymptotic for n prime AB. And then there's one more stage, which is there's a coprimality condition, which I dropped in n prime AB. So that has to be reinserted, which is a bit of a pain, but it's, I'll spare you the details of that. Okay. So in the last few minutes, I'd like to just discuss a bit the leading constant. Here is an explicit expression for the leading constant we obtained. So unsurprisingly, given our method, it's a sum over the y's. And it involves a singular integral sigma infinity y, which actually only depends on the signs of the yi. And then, yeah, so here the singular integral is basically turned into a product of local densities. Okay. So in contrast to this, we have a expression for a leading constant from the PSTV-A conjecture. And this is, okay, so in our case, it's this following expression. So this UQ thing, this is supposed to be like the topological closure of like the Campana points on X in the Adels. And then this HD is like the height corresponding to our divisor D. And then D tau X, this is the kind of usual Tamagawa measure, which pops up in the classical Manin conjecture in Pear's prediction for the leading constant. So anyway, it turns out this is just an Euler product. And we kind of think of the sigma p's. These are like integrals over, these are kind of p-adic integrals, but with some local Campana conditions. Okay, so if we try and compare C with C PSTV-A, then the thing is, like this C, we can write it as a single Euler product. It's not multiplicative in the y's. And it turns out that actually C and C PSTV-A aren't equal. However, in the formulation of the PSTV-A conjecture, they did allow for the removal of thin sets. So we've already removed a thin set T, but maybe if we remove some other thin set as well, then these constants do match up. And yeah, the answer to that is yes, although it's not very satisfactory for the following reason. The thing is, we kind of have quite a lot of thin sets here. If we take Cy to be the leading constant you get from NYB, which is counting points on this quadric QY, then each of these CYs contributes a positive proportion to the leading constant. And so CY is basically the summand we had in this expression for C at the top of this slide. But the thing is that each of these CYs corresponds to a thin set of Campana points. And to see that, we can take a morphism from the quadric to P2 as follows. And the image is a type 2 thin set in P2. And then we can intersect that with our set of Campana points. And we get this disjoint union of our Campana points as a disjoint union of the thin sets Ty. And yes, so the upshot of this is that we can actually obtain any constant between 0 and C by removing an appropriate thin set. So yes, we can obtain C PSTV-A, but we could obtain lots of other things as well. Okay, and then things kind of get worse as well. So we considered a slightly different example of squareful values of binary forms. Here we take X to be P1, and we take H to be the usual height on X. And D is the divisor, 1/2 of AX squared plus BY squared. And we assume that A and B are 1 mod 4 and they're coprime and square free for convenience. Then we consider the orbifold XD with the obvious good integral model over Z. And here's the corresponding counting problem. So I've recycled my notation here for NB. This is obviously different to before. So we're counting now the number of XYs in Z2 prim, which are bounded by B, and such that AX squared plus BY squared is squareful. And what we showed is that the PSTV-A conjecture does not hold in the above setup, in the case A equals 37 and B equals 109. And actually, we found infinitely many counterexamples. The reason it doesn't hold is because the leading constants don't work. So this is what happened. We calculated C PSTV-A here, and it's some factor R, which is basically from the real density and a few factors of pi and that kind of thing. But anyway, it's that times an Euler product. And then to find an asymptotic formula for NB, we followed basically the same approach as in the sums of 4 square fools thing. So we write AX squared plus BY squared equals U squared times V cubed. We fix the V's, count points on the conic, and then take a sum over the V's. And this is actually quite a bit easier than the 4 square fools thing we did before. And here's the expression for the leading constant that we obtained. And you can see that it's similar to C PSTV-A. So if we put K equals 1 and L equals 1 here, we get out precisely C PSTV-A. But then we also have some other things going on, at least when A and B are greater than 1. Involving some non-trivial characters here. So 37 and 109 are prime, which means that in that case, our double sum here is actually a sum over 4 things. One of them is the PSTV-A, and we kind of cooked up 37 and 109 in such a way that these Legendre symbols worked in our favor, and the sum of the other three contributions is strictly negative. This shows that C is strictly less than C PSTV-A, and then you can remove as many thin sets as you like, but that's only going to further reduce the constant C, and therefore thin sets cannot explain the discrepancy between these constants. Okay, so I'd like to just finish with a few questions this raises. I don't claim to have the answers to these. So first of all, under what circumstances precisely is the prediction of the leading constant in the PSTV-A conjecture correct? And how can we fix it in the cases where it's not? Secondly, particularly seeing we have this situation quite often where we have these accumulating thin sets, it would be quite nice to formulate a geometric prediction for what thin sets we should be removing in the spirit of the work by Lehmann, Sengupta, and Tanimoto, which they did for Manin's conjecture. And then finally, we could ask, is the kind of thing we had here just a feature of Campana orbifolds, or could anything similar possibly happen for pairs constant in Manin's conjecture? Anyway, that's everything. So thanks a lot for listening.